may have studied separable equations in your Calculus 2 course in the chapter on solving differential equations, but we'll consider this our first official technique for solving differential equations, seeing as though some of you may not have done this before. Now we know any differential equation is separable if we can write the differential equation as either the product of a function of x and a function of y, or as a quotient of a function of x and a function of y. Either way, we can then rewrite this in what we call separable form, where we have a function of y times the differential dy equals a function of x times the differential of x. So let's take a look at some differential equations and see what it is we're talking about. If we take this differential equation to get it into separable form, what we need is for this to go to the other side. Then it will be at least in derivative formula form. So moving the x squared y squared to the other side, we get this. Now we can factor the x squareds from both of these two terms, and therefore write this as the product of a function of x and a function of y. So that's how we know we've got separable form. In this one, we will subtract the 4xy from both sides and then factor, and we have our function of x and our function of y. Likewise, in differential form, we can subtract the 4y, and you notice that all we have is y's. Well, actually, there are two functions on the right. The other one is 1. So f of x would be a 1, and then the function of y would be y squared minus 4y. So if we have separable differential equations, here's how we approach that. Now these are just the steps, and then I'll show you how we do them. We want to write in separable form. We want to figure out from the separable form what the constant solutions might be. We want to get all of the y's on one side, all of the x's on the other side, and then integrate. That's our plan. Now we'd like to come out with an answer that just says y equals something. That can't always happen, but we'll give it a try. And finally, sometimes you'll see that the constant solutions are tied up in the general solution, so we don't actually list them separately. And here's what it looks like for this differential equation. Now we've already seen to write this in separable form, we put it in derivative format form first by solving for the dy dx, and then factoring to get x squared times 1 plus y squared. Now in this form, we can look at the factor 1 plus y squared to determine any constant solutions. Constant solutions would occur where the factor 1 plus y squared is equal to 0. Of course, that is not true for any real number, so we say there's no constant solutions. However, to get this in a form where we can solve it, we divide both sides by the 1 plus y squared and multiply both sides by dx, if you will, to get all of the y's on one side and all of the x's on the other side. And then we integrate both sides. Well, the integral on the left side of 1 over 1 plus y squared is the arctan of y. The integral on the right side of x squared would be x cubed over 3. the two constants of integration, the one from the left integral and the one from the right integral, can be combined into a single constant of integration. And as we said, we would like to come out with y equals something. So to solve this for y, since we have the arctan of y, we need to do the tan of both sides. So on the left, when we do the arctan of y, when we do the tan of the arctan of y, we get just y, and that comes out to be the tan of what's on the right. Now, since we're through manipulating all these constants, we'll just call it C. So there's our general solution. Now, we want to try to reconcile our constant solutions, which there are none. So there's nothing to reconcile on this one. And we pronounce the y equals tan of 1/3 x cubed plus c to be our answer. Now, I've drawn a slope field using maple and some of the solutions which would arise from different values of the c. And so this is just a visualization of what some of the answers would look like. Let's try our technique on this one. So we move the 4xy to the other side, factor. Now this time, when we take the y squared minus 2y and set it equal to 0, we actually get two constant solutions. And we'll worry about those later. We just need to recognize that there are some. And let's go on about our process. So here we need to divide both sides by y squared minus 2y and then integrate both sides. Now this is where our calculus 2 training comes in handy. On the left hand side, to do the integral of 1 over y squared minus 2y, perhaps you recognize we need to do the partial fraction decomposition. I like saying those words. Here, however, I've fudged just a little bit and done the partial fraction decomposition on my TI-89. So, on the TI-89, if I do an expand on the 1 over y squared minus 2y, I get the partial fraction decomposition. So to do the integral of 1 over y squared minus 2y, I can do these two integrals, which I recognize as being the ln of y minus 2 and the ln of y. The integral of 2x would be 2x squared over 2. Now I've already taken the liberty of taking those two constants of integration that would have resulted on the left-hand side from those two integrals and combining them together with the constant of integration on the right-hand side to just write one constant of integration, which I'll put on the right-hand side with the x's. Now, again, what we'd like to do is to come out with just y as a function of x, if at all possible. So let's go through the process from algebra of doing that. We can factor the 1/2 from these two, and then use the property of logarithms to combine the ln's. Well, when you do the ln of y minus 2 minus the ln of y, the property of logarithms tells us that we can write that as the ln of y minus 2 over y. If we multiply both sides of this equation by 2, we get this. Now notice how the C1, which I multiplied by 2, I'm now calling C2. Well, 2 times some constant is still some constant. So again, we don't need to call this 2C1. We'll just replace it with some other constant. In the end, we'll call it whatever constant we want to call it. However, let's finish it out. We need to do the natural exponential of both sides. On the left, e to the ln of y minus 2 over y just comes out to be y minus 2 over y. Okay, we multiply by y, we switch sides and factor the y, and then divide. Now again, if you follow through with the constants, you notice here we had actually an e to some constant, which happens to be some new constant. So again, all these constants kind of work their way out until in the end we just call the constant that ends up by whatever letter we want to call it. In this case, we're calling the constant a. So anyway, the last step is to reconcile this with our general solutions. We had y equals 2 and y equals 0. Well, as you can see, when this constant happens to be a 0, we'll come up with just y equals 2 divided by 1, or 2. So the y equals 2, which was a constant solution, is really part of the general solution. It's not separate. Now the y equals 0 is separate. We can't plug anything in place of the a and come up with 0 as an answer. So y equals 0 is a totally separate solution than the other. And again, here's a field plot of the differential equation with a few of the solution curves plotted. Now this is the same idea, except as you can see, we have what we call an initial value. So y of 0 equals 1. I'll go through this a little quicker. It's already in derivative form, so we just need to divide both sides by y, and then integrate both sides, and try solving for the y. Well, we do the natural exponential of both sides. Again, we can change the right-hand side into e to the x squared over 2 times e to the c1, and we can replace e to the c1 with just a constant, which we'll call capital C. So here is our general solution. Using the initial values, however, we plug in a 0 for x and a 1 for y, and we get 1 equals c times e to the 0, or c equals 1. So for this initial value problem, the constant in our general solution is actually a 1, so we come out with the specific solution, y equals e to the x squared over 2. And we wanted to begin by dividing both sides by y, and we'll go ahead and factor the right-hand side. So that's an x times y squared plus 1 divided by y, and that's in separable form. We want to move the y squared plus 1 divided by y to the other side, which means we need to flip it over. And then integrate both sides. The right-hand side is pretty easy. The integral of x dx is x squared over 2. Now the left-hand side is going to require a little bit of work. In our differential equations class, I do not mind if you use TI-89 calculators for this tedious derivative and integral work. So I'll pull out my TI-89 and do the integral of y over y squared plus 1, which is 1/2 times the ln of y squared plus 1. We'll put the constant on the other side. Now again, we want to try to solve for the y. So we will multiply through by 2, and again the constant multiplied by 2 is some new constant, so we don't put a 2c1 out here. We don't want to do the natural exponential of both sides, and subtract 1. Okay, so when we get to here, however, we're kind of stuck. We cannot recover a single function at this time. The best we can do is plus or minus the square root of that. However, it's an initial value problem, so we will continue on with reconciling our solution with the general solution. Initial values, substituting a 0 for x and a 2 for y, and then trying to solve for the c, we come up with c times e to the 0, which is c times 1, or c, square root of c minus 1, plus or minus, is equal to 2. Well, if we square both sides, it doesn't matter about the plus or minus. It's going to come out with just the c minus 1. Add 1, and we get c equals 5, regardless of the plus or minus. And so we know that the c is a 5, and for our initial value, you notice we have a positive y. So where the solution came out to be maybe plus or maybe minus, we know for our value it has to be the plus.